Let's explore the different aspects of the process. It starts with the concept definition. This is where we try to get a solid grip on the problem at hand, usually a vague set of project objectives. Think of it as trying to solve a puzzle when you only have a few pieces. From our understanding of the problem, we define a set of possible concepts or ideas to solve it. Using various techniques, we narrow it down and select the best candidate to explore further. But here's the catch. Often, the concept we choose is too complex to handle all at once, so we break it down into smaller, more manageable pieces during the system definition. Then we keep reiterating this, refining and simplifying, until we're left with elements that are simple enough to engineer. That's when we move into the design, where the components are designed in details. Now we start building the components. This is when the system starts taking shape in the physical world. Once we have our components, we integrate them into subsystems and run verification tests. This ensures that each component works as expected and meets the requirements we've defined. We do this repeatedly, checking that every part of the system is working perfectly. The next thing is to confirm that all those subsystems work together as one cohesive whole. It's like checking the connections between different puzzle pieces to make sure they fit. Finally, we reach system validation. This is the grand finale where we confirm that the system not only works in theory, but also meets the stakeholders' needs and performs as expected in the real world. This isn't just about making sure the system works technically, it's about delivering the value that was promised in the beginning. We use the V model as a way to tell a story and introduce the main activities of systems engineering, and we did so in a clean, linear way. You finish one activity and then you move on to the next. But here's the twist. Systems engineering is iterative. This means feedback from later activities often leads us to revisit earlier ones. For example, as you start designing or testing a subsystem, you might realize that the initial requirements or design concepts need to be updated. Think of it like painting a masterpiece. You step back, take a look, and refine as you go. It's a constant cycle of improving until the design is just right. Next, let's talk about recursivity. As we break down a system into smaller subsystems, the engineers in charge of those subsystems perform the same activities. You define, design, test, and validate each part of the system in detail, just like you did with the larger system. It's a cycle that repeats at different levels of granularity. Think of it like peeling an onion. Each layer is progressively more detailed, but the process is the same each time you go deeper. But it gets even more interesting with the concurrent aspect of systems engineering. In the real world, we don't design systems and subsystems one after the other, going down into the levels. Instead, everything kind of happens all at once. To illustrate, let's make the V flat and only consider the left part. We simplify it with two big domains: problem domain, which is the concept and system definition, and solution domain, which is the detailed design and implementation. Now, the activities of the process don't always follow each other neatly. Instead, it's more of an overlap because of the iterative aspect of systems engineering. Like we saw, earlier activities might be impacted by discoveries in later ones. Now let's draw the project timeline above the activities. In practice, different parts of the project move at different speeds. Some subsystems might already be deep into the design phase, while other components are still being defined or haven't even started. This pace difference is due to their complexity, how critical they are to the project, or how disruptive they are. But there's also a difference in the effort you put in different activities. For example, a well-known component that has little need for evolution will spend less time in the problem domain and focus on the design, while something completely new and disruptive will need a lot of work to understand how it works and integrates with the rest. So, while you might be working on defining requirements for one part of the system, another team might already be designing a component or testing a subsystem. This is concurrent engineering, things happening in parallel, not just one after the other. This concurrency means that systems engineers have to juggle multiple tasks and coordinate teams to keep everything in sync. It's not just a handoff from one phase to the next, it's a continuous, overlapping process where things are happening all at once. So we've seen all activities related to the development of the product, but we're not done yet. Systems engineering doesn't stop once we've built the system. That's just part of its journey. Now, we enter the deployment activities. Sounds a bit like the end of a movie, right? But this part is just as important as everything that came before it. First, we have transition. This is where the system is handed off from the development team to the operational team. It's like passing the baton in a relay race. The goal here is to ensure a smooth handover, making sure the system is ready for real-world use. Then comes operation. This is where the system starts doing its job. Whether it's a spacecraft orbiting Mars or a high-speed train, it's time for the system to deliver on all those promises made in the design phase. But even the best systems need maintenance. Over time, components wear out, new tech is introduced, or the environment changes. Maintenance ensures the system stays up and running efficiently, avoiding unnecessary downtime or worse, complete failure. And finally, disposal. It's all about responsibly retiring the system. Whether you're recycling parts, decommissioning equipment, or ensuring that the system no longer poses any environmental or safety risks, proper disposal is key to closing the loop. These last activities are crucial because it ensures that the system lives up to its purpose, stays efficient, and, when its time is up, is responsibly retired. So as you can see, systems engineering isn't just about creating something. It's about making sure that something works well for the long haul and doesn't leave a mess behind when it's done. And one last thing, we decided to show you the activities of systems engineering using the V model for education purposes. We found it easier to introduce the iterative, recursive, and concurrent aspect of systems engineering starting from the V. We hope that even if the graphics are linear, you now understand that in reality, everything happens everywhere, all at once. In the literature, you may find different representations, such as the one shown here. But rest assured, the activities remain the same, and this is what's great about systems engineering. It's adaptable to both the product and the organization developing it.